Cold drawn seamless steel tubing subjected to internal pressure has a diameter equal to 60 mm and the wall thickness equal to 2 mm. Ultimate strength of the steel is equal to 360 megapascal. Bursting pressure you have to calculate. To calculate the bursting pressure, we have to equate the value of the ultimate strength is equal to hoof stress, because the thin cylinder is designed on the basis of the hoof stress. So in this case, we have given the diameter D is equal to 60 mm. Wall thickness T is equal to 2 mm. And we have given the value of SYT. This value of SYT will take same as equal to the hoof stress, that equal to sigma h, which is equal to 360 megapascal. The maximum stress will be same as equal to the hoof stress is equal to pressure multiplied by diameter D and is divided by 2 times of thickness. Hoof stress will substitute same as equal to ultimate stress, then only the pressure will be the bursting pressure. So we have sigma h is equal to 360. Pressure you have to calculate. Diameter you have to take same as equal to 60 and is divided by 2 times of wall thickness, that equal to 2 mm. So the bursting pressure this time will come out to be 24 megapascal. A cylindrical water tank of height equal to 20 meter, inside diameter equal to 2 meter, vertical axis is open at the top. Permissible stress for the tank material is 70 megapascal. If the efficiency of a longitudinal joint is 70% and the efficiency of circumferential joint equal to 80%, then the thickness of the tank, if the tank is full of water, in mm we have to find out. So let's consider this one is representing the vertical cylindrical tank, and the height of this tank is completely filled with water and the height of the water is given as 20 meter. The vertical axis is open at the top and the permissible stress for the tank is 70 megapascal. That value will assign to the hoof stress. So we have sigma h is equal to 70 megapascal. Inside diameter is also given and we have inside diameter is equal to 2 meter. In addition to that, we have given the longitudinal efficiency. So we have eta L will be equal to 70%. We only required eta L in the calculation of sigma h. The maximum possible pressure will be at the bottom point A. So we'll calculate what is the pressure at point A. To calculate the pressure at A, we'll use the fluid formula, that is we have rho multiplied by G multiplied by total height equal to H. Density we will take standard value equal to 1000. Acceleration due to gravity is 9.81 and we have total height is equal to 20 meter. This will give you gauge pressure in Pascal and we'll get this value is close to 2 into 10 to the power 5 Pascal, or this value is close to 0.2 megapascal. And now we can use the formula for hoof stress. We have hoof stress is equal to pressure multiplied by internal diameter di. We have to take the pressure at point A is further divided by 2 times the wall thickness and is again divided by the longitudinal efficiency. Hoof stress here is equal to 70 megapascal. Pressure we also put up in megapascal, that equal to 0.2. We have internal diameter is equal to 2 meter, so that you have to use in mm is 2000 mm is divided by 2 times the wall thickness and we have wall thickness to be obtained. Longitudinal joint efficiency is 0.7. Solve this, you will get the required thickness T. The required thickness T will come out to be 4.08, that will be mm. This question will take from the GATE 2008 exam. A cylindrical container of radius r equal to 1 meter, wall thickness equal to 1 mm is filled with the water up to depth of 2 meter. This is shown in the figure. We have diameter is equal to 2r and we have given the radius r is equal to 1 meter. Total depth h is equal to 2 meter. And the density of water you have to take as 1000 kg per meter cube. Acceleration due to gravity you have to take as 10. So we have density rho is equal to 1000 kg per meter cube. And the acceleration due to gravity, that equal to g, you have to take as 10 meter per second square. The self weight of the cylinder you have to neglect. The formula for hoof stress in the thin wall cylinder can be used at all points along the height of the cylindrical container. So the clue is given here. Hoof stress formula is PD divided by 2T, but the pressure is variable as the depth will change. In the first part, you have to calculate the axial and the circumferential stress experienced by the cylinder wall at the mid depth. That is, at this point you have to find out what is the axial and the circumferential stress. So let's mark here this depth first. So this depth will represent as by point A. Since here the total height is equal to 2 meter, so this depth here will be equal to 2 minus 1, that will be equal to h equal to 1 meter. So you have to first calculate what is the pressure at point A. Once you calculate the pressure at point A, we can calculate the axial and the circumferential stress. In the second part, the Young modulus and the Poisson ratio of the container material are 100 gigapascal, and point 3, the axial strain in the cylinder you have to calculate. So for that purpose, we'll draw the state of a stress, and then using the generalized Hooke's law, we'll calculate axial strain in the cylinder. So first we calculate what is the pressure at point A. That will be due to the column H. So we have pressure at point A will be the product of rho multiplied by G multiplied by depth equal to H, that is up to point A. Density you have to use is equal to 1000. Acceleration of gravity you have to use as 10. Depth is equal to 1. This answer will be Pascal, and this value represents the gauge pressure. So we required the gauge pressure here, but we required in megapascal. So this pressure is equal to 10 to the power 3 and 10 to the power 1, that equal to 10 to the power 4 Pascal. So divide it by 10 to the power 6, and we will get the pressure PA is equal to 10 to the power 4 divided by 10 to the power 6 is 0.01, that will be megapascal. So we know the pressure at A, that equal to 0.01 megapascal. So we calculate the axial and the circumferential stress at the midspan. Axial stress is represented by sigma L and is given as pressure multiplied by diameter D. We have to take the pressure at point A, that is at midspan, is divided by 4 times of the wall thickness T. Pressure you have to take in megapascal is 0.01. Diameter will be equal to 2 times of r, that is 2 meter. We have to take in mm is 2000 divided by 4 times, and we have thickness equal to 1 mm. So we have 20 divided by 4. So this equal to 5 megapascal. In a similar way, we can calculate the circumferential stress, that equal to sigma h, and we have sigma h equal to pressure at A multiplied by diameter D divided by 2 times of T, or you can calculate the hoof stress as 2 times of sigma L, that is we have 2 times of 5, which is equal to 10 megapascal. So you have to follow the sequence here. First is axial and then is circumferential. We have axial is 5 and the circumferential equal to 10, 5 comma 10. 5 comma 10, choice B is correct in the first part. In the second part, the Young modulus and the Poisson ratio are given, and we are interested to know the axial strain in the cylinder wall at the mid depth. That is, at same point we have to find out the axial strain. This time we have axis is along the y-axis and the circumference will be along the x-axis. So we'll represent here the state of a stress along the x direction. This time we have sigma x will be the equal to hoof stress, and we have value of hoof stress equal to 10 megapascal. Along the y direction we have the axial stress, that is equal to sigma L, and this value of sigma L is equal to 5 megapascal. This one is representing the state of a stress at mid depth, and we are interested to know the axial strain. Axial strain is epsilon y. So if I apply the generalized Hooke's law, I will get epsilon y equal to sigma y minus mu times sigma x plus sigma z. Sigma z you have to always take equal to 0 and is divided by Young modulus E. Let's substitute here. Check your sigma y is equal to 5. So we have 5 minus mu mu is equal to 0.3, so 0.3, and we have sigma x is equal to 10. Sigma z you have to make equal to 0, divided by Young modulus is 100 gigapascal, 100 into 10 to the power 3 megapascal, to get your answer dimensionless term. So we get a strain along the y direction, that is the axial strain. So we have axial strain will be equal to 2 into 10 to the power minus 5 will be mm per mm. 2 into 10 to the power minus 5. 2 into 10 to the power minus 5. Choice A is correct choice. A thin walled cylinder as shown in this figure. We have radius r and the thickness d is open at both ends, and the cylinder is horizontal. If the cylinder is horizontal and is open at both ends, then the weight component will not come in picture, and in this case the sigma L will be equal to 0, and it fits snugly between the two rigid walls as shown in the figure under the ambient condition. The material of the cylinder has a Young modulus equal to E, Poisson ratio equal to mu, coefficient of thermal expansion alpha. What is the minimum rise in the temperature delta T of the cylinder? Assume uniform cylinder temperature with no buckling of the cylinder required to prevent the gas leakage if the cylinder has to store the gas at an internal pressure of P above the atmosphere. Let's take here the length of the cylinder is equal to L, and this cylinder is subjected to pressure P above the atmosphere, so we have gauge pressure equal to P. Now since here both the ends are open, we have longitudinal stress, and this longitudinal stress will act along the x direction and the hoof stress will act along the y direction. So the longitudinal stress will be same as equal to sigma x, and this value of sigma x will be equal to 0. But it is subjected to the pressure P, therefore we have a stress along the y direction that will be equal to the hoof stress sigma h is equal to sigma y, and is given as, we'll use here PRT form. So we have pressure multiplied by radius r and is divided by thickness equal to T. Now because of the two stresses produced here, that is sigma x and sigma y, there is a strain is produced. So let's calculate here axial strain. Axial strain will be same as epsilon x. Epsilon x is equal to sigma x minus mu times sigma y. Sigma z in the case of thin cylinder is always equal to 0, is divided by Young modulus E. Now this time the value of sigma x is equal to 0. Value of sigma z equal to 0. So what we observed here is that we are getting the strain as a negative value. It means that the length will going to decrease. So we have epsilon x, that is the axial strain, equal to minus mu into sigma y, which is pressure multiplied by radius r and is divided by T, and further divided by E. T and E. Now because of there is a change in length, that is the length will going to decrease, then the gas will leak. It means that we have to expand this by increasing the temperature, and it should produce the thermal strain, and because of that thermal strain the length has to be increased. In that case the gases will not leak from the pressure vessel into the atmosphere. So since the value of epsilon x is negative, the length decreases, and as the length decreases there will be gas leakage. We want to avoid the gas leakage here, so what we'll do, we'll develop here a thermal strain by increasing the temperature delta T. So to avoid the leakage here, increase the temperature by delta T so that it will produce the positive strain, and in that case we have epsilon x plus epsilon thermal. If this total value will be equal to 0, then there is a no leakage, and the thermal strain is given as alpha multiplied by delta T. So we have epsilon x is given as minus mu into pressure P multiplied by radius r divided by T divided by Young modulus E. The thermal stress is known to us is alpha into delta T, and if we divide it by E, you will get the thermal strain epsilon T. So we have to put the value of thermal strain equal to alpha multiplied by delta T, and this sum must equal to 0. If this sum is equal to 0, it means that dl will be equal to 0. If dl equal to 0, we will maintain the length, and if we maintain the length, there is no leakage from the cylinder into the atmosphere. We have to find out here the value of delta T. So we have delta T will be equal to, this term will become positive, is mu into pressure P multiplied by radius R divided by alpha multiplied by thickness multiplied by young modulus E. Mu into P into R divided by alpha TE. So these two are wrong. Choice D is correct. Mu into P into R divided by alpha times T multiplied by E. Choice D is correct choice. A thin walled cylindrical can with a rigid end caps has a mean radius R equal to 100 mm. So we have shown here dotted line, and that will be the mean radius equal to R. Wall thickness T is equal to 5 mm. So this total value will be equal to R, and if we are taking here the internal radius, that will be R minus T by 2. So we have inner radius R will be equal to capital R minus T by 2. We have capital R is equal to 100, and we have thickness equal to 5 divided by 2. That is, we have 100 minus 2.5 is 97.5 mm. Here this small value is T by 2. The can is pressurized and an additional tensile stress of 50 megapascal is introduced. So this one is extra stress is imposed, that equal to sigma A along the axial direction, that is along the x direction. So this direction will treat as x, and the vertical direction is equal to y. So we have axial stress is produced along the x direction and the hoop stress is produced along the y direction. Assume that the state of a stress in the wall is uniform along its length. If the magnitude of the axial and the circumferential component of the stress in the case are equal, he says that whatever the stress is produced in the y direction and the total stress produced along the x direction, which is consist of axial plus the tensile stress equal to sigma A, that are equal, then what is the value of pressure P you have to find out. So let's represent here the state of a stress. Horizontal axis is our x axis, vertical axis is our y axis. In this case, we have total stress acting along the x direction is the axial stress, that is the longitudinal stress, plus we have additional tensile stress equal to sigma A, and along the y direction we have sigma y, and that equal to the hoop stress sigma h, and this value of sigma h is same as equal to 2 times of sigma L, always true. He says that the magnitude of the axial, that is sigma x, and the circumferential component are equal, that is sigma y. So in this case we'll equate sigma x with sigma y. Sigma x here will be equal to sigma L, plus we have axial stress sigma A, which is equal to 50, and sigma y is sigma h is 2 times of sigma L. So this sigma L will shift to the right side. We will get sigma L is equal to sigma A, and we know the longitudinal stress is given as pressure multiplied by the radius R divided by 2 times of thickness is equal to sigma axial. Pressure we have to find out. So we have pressure P is equal to sigma axial is equal to 50 megapascal. We have 2 times the thickness T, and we have thickness T is equal to 5. We have inner radius R is equal to 97.5. So we will get this value close to 5.128. That will be megapascal. So we require the pressure here is 5.128 megapascal. The video you are watching is from the app, which is the Mohod class app available on Google Store. And in this app, we'll cover all subjects involved in mechanical engineering for GATE. Join the course directly from your mobile. The link is given here.